All right, guys, welcome back. Today we're stepping into part 2 of our Geometry full course series. We're in section 1 of chapter 1, and we're jumping over here to our second example. We ended our last video with our first example. So let's take a look at part A here, on number 2. All right. Part A is asking us to draw and label a segment with endpoints U and V. So to draw a segment, we put 2 dots, one for U, one for V, and then we connect them with a straight line. Because this is a segment, not a line and not a ray, the line will stop at the dots. So the line stops at the dots and it has no arrows on the ends. And to name the segment, we write either UV or VU. Order does not matter here, with a small bar on top. Either name is correct. Segment UV or segment VU. Now let's look at part B. Part B asks us to draw and label opposite rays with a common endpoint, Q. So remember, opposite rays share an endpoint and together they form a straight line. Now the textbook shows 3 points here, P, Q, R, on a horizontal line with Q in the middle. Q is our common endpoint. From Q, one ray goes left through P, and from Q, the other ray will go right through R. Together they form one straight line with arrows on both ends. And these opposite rays with a common endpoint form our line. So we have ray QP, and we have ray QR. Now when we're naming them, the endpoint Q must come first in both names because Q is the starting point of each ray, so order does matter. All right, so let's write that down. We have ray QP, and we have ray QR. They both will go in the same direction. My apologies. And our common endpoint is Q. Now in the textbook, we see them all joined together to make the line. So for example, if I write ray PQ, would that be right? No. The common endpoint Q must always be the first letter. Order does matter here. All right, let's go to our check it out problem here. Draw and label a ray with endpoint M that contains N. So we draw our dot and label it M. This is the endpoint, and then we draw a second dot to the right and label that N. Then draw a straight line starting at M going through N with the arrow at the end. All right, so we put the arrow on the far end there because it's going in that direction. And we want to show that the ray keeps going on forever in this direction. That's what the arrow is for. And that's how we get that ray. How would we write that? Ray MN, this shows it's a ray. All right, so we want to make sure that we write M first as the endpoint and N second is what's really important there. All right, on to our first 3 postulates. That's what geometry is all about, right? Postulates. Here are our first 3 to get us started. These are 3 very important facts in geometry. That's what postulates are. A postulate, also called an axiom, is a statement that we accept as true without having to prove it. So we just agree that it's true, and then we use it to figure out everything else. So think of postulates like the rules of a board game. You don't have to prove the rules are true. You just agree to play by them. That's what math really is all about in general. For example, when Newton sat down and wrote calculus, he was looking for a way to define the universe with a set of rules, and that's really where math comes from. Now in geometry, the postulates are about points, lines, and planes, which we talked about previously in our last video. These are the rules that we're using to describe how shapes work. All right, so a postulate or an axiom is a statement accepted as true without proof. Now let's take a look at each one here on our board. Here you are with 1, 1, 1. It says that through any 2 points, there is exactly one line. So that means if you pick any 2 dots, you can always draw exactly one straight line through both of them. No more, no less. So there's only one way to connect 2 points with a straight line. And here is our visual example. So if you put, for example, 2 pins on a board and you want to lay a string straight across them, there's only one way to do that. That's a real-world example. All right, let's go to 112. Postulate 112 says through any 3 noncollinear points, there's exactly one plane containing them. Now remember, noncollinear means the 3 points do not all sit on the line or on one line. So if you have 3 points that are not in a straight arrow, there is only one flat surface that goes through all 3 of them. This is why a tripod or a 3-legged stool never wobbles, for example. 3 feet always sit perfectly flat on the ground, but a 4-legged chair can rock if one leg, for example, is just slightly shorter. Here is our visual. There are 3 dots there in that parallelogram. 113. Postulate 113 says, if 2 points lie in a plane, then the line containing those points lies in the plane. So if I pick any 2 points on a flat surface and I connect them with a straight line, that whole line stays flat on that surface. It doesn't go up off the surface or below it, for example. Let's trace the line that goes through our parallelogram here. It stays 2-dimensional. So for a real-world context, we can think of a piece of yarn that's pulled tight between 2 pins on a flat table. It'll always lie flat on that table. It can't go above or below the table because of the laws of physics. All right, let's take a look here at example 3. I'll zoom in here just a bit. We're asked to name a line that passes through 2 points. So here we can see in the diagram on the right, a flat surface. This is plane R. So it's written with a script letter R. There's our script letter. And inside that plane, there are 3 points, G, H, and F. There's also a vertical line drawn through G and H. And that line is labeled with our lowercase n. So which line passes through the 2 points G and H? It is line N. By postulate 111, which we just took a look at, we know there is exactly one line that goes through any 2 points, and that one line is line N. Here in example 3. All right, so again, there is exactly one line, line N, that passes through G and H points here in our parallelogram. And then our check it out, number 3, name a plane that contains 3 non-collinear points. So here's our diagram. We have 3 points, G, H, F, as we just discussed. Are they all on one straight line? G and H, for example, are on line N, but F is off of line N. So the 3 points G, H, F are not all on one line. They are non-collinear. Let's take a look at postulate 112. By postulate 112, 3 non-collinear points determine exactly one plane. We can name that plane using the 3 points plane G, H, F. That's one possible answer here, GHF. Now remember, any order of the 3 letters is fine. We could write plane FGH or plane FG, etc. They all name the same plane. We could also call it plane R, since the diagram already labels the plane with that script letter. All right, let's go on to example 4, where we're going to discuss 2 more postulates. Intersection of lines and planes. So we need a new word here, intersect. Here's our word intersect, intersect. Now, two figures intersect if they share one or more points. The set of points they share is called the intersection. In algebra, you may have learned that the solution, if you've taken algebra or pre-algebra, that the solution to a system of equations is where the graphs cross. That specific crossing point is an intersection. So it's the same idea here in geometry. When two lines cross or two planes cross, the place they have in common is the intersection. And you may have been discussing these types of things, for example, in coordinate geometry, which is examined alongside algebra. Like, for example, you start learning about the coordinate grid in 5th grade. All right, so an intersection are the points two figures share. Let's keep that in mind as we continue on to our postulates. Postulate 114 says that if two lines intersect, then they intersect in exactly one point. So when two straight lines cross, they only cross in one single spot. Two straight lines cannot meet at two different places. I'll circle here in the diagram. Here's a point where they meet, and here's a point where they meet. Now imagine two perfectly straight roads that can only cross at one intersection. They can never cross twice, for example. Now let's look at 115. If two planes intersect, then they intersect in exactly one line. When two flat surfaces cut through each other, the place they share is a whole straight line, not just a point. So, for example, think of opening a book and standing it up like a tent. The two pages are like two planes, and where they meet, the book's spine is a straight line. That's their intersection. Let's take a look at the diagram here. I can draw my two lines where they're intersecting here at that point. Now let's look specifically at the textbook problems here. We're sketching figures here that show each of the following: a line intersecting a plane. It intersects a plane, but it does not lie in the plane. So here we have a flat parallelogram as our plane called R. And the vertical line. So line L comes down from above the plane, passes through the plane at point G, and continues down below the plane. So the line touches the plane only at point G. Line L and plane R intersect at point G is how we can say that. So a vertical line passing through plane R at one point G. The line crosses through the plane. It does not lie flat on it, is what we want to get from that. Now let's take a look at B. Two planes intersect in one line. So here we have two parallelograms, or two planes, in other words, that are crossing each other. And where they cross is shown by a straight dashed line that I traced over just a minute ago. That dashed line is the intersection. So we use a dash style for the part of the line that is hidden behind one of the planes to show that more visually. Let's do that again. 1 and 2. And now we can write one plane is joined together to the other plane. They intersect with a single line here. So two parallelograms or planes crossing each other. The line where they meet is shown as a dashed line. Now let's go to our check it out part. Sketch a figure that shows two lines intersect in one point in a plane, but only one of the lines lies in the plane. Here we can go over a little bit to the right here. So only one of those lines lies flat on the plane. Let's zoom in a little bit. So here's our flat parallelogram. This will be the plane. And we want to draw a horizontal line that lies inside the parallelogram with arrows on both ends. That's here. That is the line inside of the plane. Then we can draw a second line that goes up, out of the plane, and down through it, crossing the first line at one point. We'll also put two arrows on both ends of the second line. There's that one. So the two lines cross at one point inside the plane, but only the horizontal one stays flat on the plane. And what's important here to know is that only one line lies in the plane. All right, so again, a correct sketch would have a parallelogram, the plane, one line drawn flat inside the parallelogram. This line lies in the plane. A second line that crosses the first at a single point but goes up out of the plane. It does not lie in the plane, but both lines have arrows on both ends. All right, let's go to our think and discuss section. Number 1, explain why any 2 points are collinear. Well, we go back to postulate 111. Through any 2 points, there is exactly one line. So anytime we pick 2 points, they end up on one line together. And the definition of collinear is on the same line. So any 2 points are always collinear. So how would we write that out? Let's answer in complete sentences here. So we can say by postulate 111 through any 2 points, there is a line. Therefore, any 2 points are collinear. It has 2 L's. There we go. There's our answer for number 1. We'll walk that out. Number 2, which postulate explains the fact that 2 straight roads cannot cross each other more than once? Let's go to postulate 114. All right, because it says that if 2 lines intersect, they intersect in exactly 1 point. 2 straight roads are like 2 straight lines. So we'll put postulate 114. Just put dashes there. 114. There we go. Number 3, explain why points and lines may be coplanar even when the plane containing them is not drawn. All right, let's take a look at 112. Any 3 points that are not on the same line determine exactly one plane. Okay. So even if the plane is not sketched in the picture, it still exists. The points are still coplanar. Let's go back to our number 3 here. So we can write any 3 non-collinear points determine a plane. So a plane always exists for 3 such points, even when the picture doesn't show it. We can write those in our own words. Let's make it simple. For the sake of time, let's just say any 3 non-collinear points determine a plane. So a plane always exists for 3 such points, even if the picture doesn't show it. You could write that down as well if you like. Number 4, name all the possible line segments and rays for the points A and B, then give the maximum number of planes that can be determined by these points. So with just 2 points, A and B, we have one line through A and B, but we can call it line AB or line BA, right? There's one segment called segment AB or segment BA, and there are 2 rays, ray AB and ray BA. So the number of planes determined by only 2 points is 0. Again, from 2 points, we can name line AB and line BA, same line, 2 names. Segment AB and segment BA, same segment, 2 names. Ray AB and ray BA, these are different rays. They go in opposite directions. For planes, we need at least 3 noncollinear points to determine one plane. So 2 points alone gives 0 planes. Let's go ahead and write that out. We'll say line AB, line BA, segment AB, segment BA, ray AB, ray BA, and the maximum number of planes is 0. All right, so 2 points always lie on infinitely many planes. Any plane through that line works. So we say the 2 points alone do not determine a unique plane. That's why the answer here is 0. All right, and then our number 5 here, the last problem, before we jump over to our exercise set, will be a graphic organizer. So let's throw in our undefined terms that we've been talking about throughout these past few videos. In the left box, we can write point. This is a location with no size. So for example, we might have point G. Okay, what about the middle box? Let's write line. We'll define that, a straight path with no thickness that extends forever. A straight path with no thickness that extends forever. Okay. Now we can draw a horizontal line with arrows on both ends. Let's label that XY. And then we have on the right a plane, a flat surface with no thickness that extends forever. All right, a flat surface with no thickness that extends forever. And we could have our parallelogram. And we could throw in, maybe I have to make that a little smaller. Zoom in here a bit. We could have A, B, and C. And then we'd have our script letter R. If we go back and see a visual, that's a nice one drawn there for us with GH and F with our script letter R there to show it's the plane. All right, guys, that will do it. Thanks for tuning in today to a little bit longer video. We are now done with 1.1, the full lesson, and we will move on to our exercises in our next video. See you soon. Bye.